Have you ever stood on a beach watching the waves? Well, you see the water rush up the shore. It soaks into the sand and seems to vanish. It is a lovely, simple sight, but it can lead to a rather puzzling question. If the sand on the beach can soak up so much water, why doesn't the whole ocean just drain away? It seems as if the sea is sitting in a giant colander. One might imagine the water slowly, but surely trickling down into the heart of the earth. It is a wonderful thought, born from a simple observation. This idea, this beach myth, is quite common. It makes a certain kind of sense. We build sandcastles and watch them crumble as the tide comes in. The water seeps underneath, weakening the foundations until the walls collapse. So, the great, wide ocean should be no different. But the ocean, of course, does not drain away. It has been here for billions of years. Let us look more closely at that sand on the beach. Let us look more closely at that sand on the beach. When a wave breaks, its water spreads across a thin layer of loose sand grains. These grains are tiny fragments of rock and shell, worn smooth by the relentless motion of the sea. Between each of these grains, there are tiny, empty spaces. Scientists call these spaces pores. When water washes over, it quickly fills these pores. This is why the sand appears to drink the water so readily. The water is simply occupying the empty spaces that are already there, just beneath the surface. This process is what we call permeability. The loose sand on the beach is highly permeable. It allows water to pass through it with ease. If you pour a bucket of water onto dry sand, it will sink in almost instantly. This reinforces the idea that the ocean floor must be like a giant sieve. But the sand you are standing on is a very special case. It is constantly being churned and shifted by waves and by wind. This action keeps the grains loose. However, this phenomenon is incredibly shallow, a delicate blanket draped over what lies beneath. Now let us leave the familiar shore venture into the deep ocean. As we travel away from the land, the seafloor changes dramatically. The sandy bottom of shallow coastal waters gives way. For a start, the ocean is immensely deep. The average depth is nearly 4 kilometers. In the deepest trenches, it can be more than 11 kilometers. All that water exerts a colossal weight. That pressure profoundly affects the ocean floor materials. Over millions of years, a constant rain of material drifts down the remains of tiny marine creatures, fine dust blown from the continents, clay particles washed out by rivers. This material settles, forming thick layers of sediment. Under the immense pressure, sediments are squeezed together. The pore spaces are compressed until almost gone. The soft ooze becomes dense, compacted mudstone and shale. This compaction creates layers that are remarkably impermeable. A basin lined with dense, water-resistant clay and rock, ensuring its water remains held within its vast basins. Beneath all the layers of compacted sediment lies the true foundation of the ocean floor: solid rock. This is the Earth's crust. The crust beneath the oceans is different from the crust that forms our continents. It is known as oceanic crust, and it is primarily made of a dark, dense volcanic rock called basalt. This rock is formed at mid-ocean ridges, where molten magma from the Earth's mantle rises, cools, and solidifies. This process is happening continuously, creating new seafloor. Basalt is not like a sponge. It is a hard, crystalline rock. While it can have cracks and fractures, it is fundamentally non-porous. Water cannot simply soak into it as it does with sand. Over time, any cracks that do exist tend to get sealed. This layer of basaltic crust is, on average, about 7 kilometers thick. It is the planet's ultimate plumbing seal. The combination of compacted, impermeable sediments on top and the solid basaltic crust below creates a two-layered defense against any significant leakage. It is true that some water does enter the oceanic crust. At mid-ocean ridges, seawater can circulate through a network of cracks, getting heated by the underlying magma. This process is called hydrothermal circulation, and it famously gives rise to deep-sea vents, or black smokers. However, this is not a one-way drain. It is a circulation system, not a leak. Even if there were small leaks in the ocean floor, the sea has a magnificent way of refilling itself. This system is known as the water cycle. It connects every drop of water on our planet. It's a constant dynamic engine powered by the sun. It begins when sunlight warms the vast ocean surface, turning liquid into invisible water vapor. The moist air rises into the atmosphere. Higher up, it cools. Cooling makes vapor condense into tiny liquid droplets or ice crystals. Droplets gather to form clouds. Winds carry those clouds around the globe. They travel for hundreds or thousands of kilometers. Eventually, droplets get too heavy to stay aloft. They fall as precipitation, rain, snow, or hail. Much of it falls straight back into the ocean. A great deal flows into streams and rivers. And where do rivers ultimately lead? With few exceptions, they flow downhill, pulled by gravity back to the sea. So the water cycle acts as a balancing mechanism. For water lost to the deep earth over geological time, enormous volumes are returned through evaporation and precipitation. The ocean is never in danger of running dry. The very existence of our oceans is tied to another grand planetary process: plate tectonics. The Earth's rigid outer layer, crust upper mantle, is not one solid piece. Instead, it is broken into massive interlocking pieces called tectonic plates. They are in constant, slow motion, floating on the hotter, more fluid mantle beneath them, moving at about the same speed your fingernails grow. This slow dance shapes the entire surface of our world. Ocean basins are not static, created, shaped, destroyed by the movement of plates. At mid-ocean ridges, creating new oceanic crust, making the ocean basin wider. Conversely, plates collide elsewhere. A dense oceanic plate collides with a lighter continental plate. The oceanic plate bends and slides beneath the continent into the mantle. This is subduction. It creates the deepest parts of the ocean. These colossal movements ensure there are always large, deep basins on Earth's surface. Without plate tectonics, Earth's surface would be much flatter. Dynamic plate shifting creates dramatic topography. High continents, deep ocean basins. That arrangement keeps water contained in vast, specific reservoirs. There is one final, fundamental reason why the ocean stays put: gravity. It is the most familiar of all the forces. It keeps our feet on the ground. It holds the moon in orbit around the Earth. Gravity pulls everything with mass towards the center of the planet, and water has mass, a lot of it. The world's oceans contain over 1 billion cubic kilometers of water. They weigh more than 1.3 billion trillion tons. Gravity exerts an immense, constant pull on this entire mass. Water, being a fluid, always flows to the lowest possible level. One might wonder if the Earth's spin could fling the water off into space, but gravity is far, far stronger. It holds our oceans. It holds our atmosphere firmly in place. This gravitational embrace makes our planet habitable. Without it, water and air that support life would be lost to space. Gravity is the ultimate guardian of our blue planet. Seeing water sink into beach sand is a tiny, localized event. On a planetary scale, it pulls the colossal mass of the ocean down into the basins that hold it. Our understanding of the deep ocean is still in its infancy. For most of human history, the seafloor was a complete mystery, a realm of darkness and speculation. Today, we are living in a golden age of ocean exploration. We have remarkable new technologies that are allowing us, for the first time, to map and study this hidden world in extraordinary detail. Autonomous underwater vehicles can now glide through the depths for weeks at a time, collecting data on a massive scale. These robotic explorers are equipped with advanced sonar, sensors that can measure temperature, salinity, and the chemistry of the water. They are giving us a high-resolution picture of the very processes we have discussed. We can see the compacted sediment layers, identify the basaltic crust, and even watch hydrothermal vents in action. This technology helps us confirm that the ocean floor is indeed a secure container, not a leaky sieve. Looking ahead, the next generation of deep-sea technology promises even greater discoveries. Scientists are developing new ways to drill into the ocean floor, to study the deep biosphere, life within rock and sediment itself. They are deploying fiber optic cables on the seafloor that can detect tiny seismic movements and pressure changes, turning the seafloor itself into a giant environmental sensor. These innovations will help us understand the subtle interactions between the ocean, the crust, and the life they support. Understanding the Earth's systems is vital for our own survival. The ocean is the planet's primary life support system. So the next time you stand by the sea, remember the deep and complex world that lies beneath the waves. A world of immense pressure, ancient geology, and perfect balance. A world we are only just beginning to truly know.